Welcome to today's Explainer. Right now, we're going to completely shatter the illusion of the internet as some kind of modern magic. Think about it. You send a high-resolution photo to a friend on the other side of the planet, and boom, it arrives in milliseconds. That feels like pure magic, right? We interact with this invisible web every single day. We're streaming movies, processing payments, firing off emails, yet for most of us, it's a total mystery. Just picture the sheer volume of data moving invisibly at this exact second, circling the globe millions of times over. Well, our goal today is to pull back the curtain on that invisible miracle and reveal the highly structured, tangible system that makes all this global connectivity possible. If you've ever wondered what actually happens in the blink of an eye, the moment you hit enter on your keyboard, you are in the right place. We're going to deconstruct the digital handshake.
So, here is our roadmap for today. First up, we'll see why the cloud is a myth. Second, we'll follow the journey of a data packet. Third, navigating with IP addresses. Fourth, the TCP digital handshake. And finally, connecting the World Wide Web.
All right, let's hit stop number 1. The cloud is a myth, where we are grounding the internet in reality.
We really have to start by busting a massive misconception that completely obscures how our everyday tech actually works. When we hear the word cloud, it naturally paints this picture of something fluffy, invisible, and floating ethereally somewhere above us. But the internet is absolutely not a magical, ethereal cloud. The truth? The cloud is mostly just a brilliant marketing term for someone else's computer. Instead of some vaporous network in the sky, we are talking about massive sprawling data centers. Think giant warehouse-sized server farms that are just consuming staggering amounts of electricity around the clock. So the key takeaway here is that the internet isn't some abstract concept. It's a meticulously designed, highly structured, and profoundly physical reality. To really demystify it, we gotta stop thinking of the internet as weather and start thinking of it as an immense, heavily industrial machine.
Now, that giant machine can basically be broken down into two very distinct halves. The physical architecture, contrasted directly against the logical architecture. On the physical side, you have the tangible components you can actually touch. And here's a wild fact for you. 99% of all international data traffic doesn't actually go through satellites in space. Nope, it's transmitted via thick, physical submarine cables lying directly on the ocean floor. We are talking about thousands of miles of fiber optic cables sitting at the bottom of the sea, which, by the way, occasionally get chewed on by sharks. That just shows the incredible physical vulnerability of the whole network. But obviously, cables and routers alone don't make a functional system. On the flip side, we have the logical architecture. These are the unseen codes, the essential communication protocols, and the rigid mathematical rules required to actually make sense of the light pulsing through those underwater cables. Both this highly physical hardware and the precise logical rules have to work in absolute perfect harmony to support the web as we know it.
Moving right along to part 2, Journey of a Data Packet, the hero's journey of information.
Let's actually personify a single, invisible piece of data and follow its adventure chronologically. But before we do, what even is a packet? Well, when you send an image or request a video, that file isn't just sent as one giant continuous chunk. It gets aggressively chopped up into millions of tiny digital puzzle pieces. Each one of those pieces is a data packet, and every single packet gets sent out on its own separate high-speed journey across the globe, bouncing between routers, only to meticulously reassemble itself once it reaches the end. It all starts at step 1, right there at your personal device, your computer. From there, it enters step 2, which is the complex routing stage driven by IP addresses. Then it faces step 3, a really critical negotiation phase known as the TCP handshake. And finally, if everything goes exactly right, it reaches step 4, the World Wide Web. Every single time you load a page, this exact journey happens for millions of fragmented puzzle pieces. It's wild.
Which brings us to section 3, navigating with IP addresses, demystifying the routing maze.
So as our little data packet departs your computer, it immediately faces a pretty complex trial, figuring out exactly where it needs to go across this massive global network. Enter DNS. DNS is the system that translates the human-friendly web names that we type into our browsers into the numerical IP addresses that computers actually use for routing. See, computers don't understand words the way we do. They need precise numbers to navigate. You can think of DNS kind of like a massive, incredibly high-speed postal phone book. It gives our packet the exact physical IP address it needs to find its target. And the scale and speed of this, truly mind-blowing. This phone book lookup happens in mere milliseconds. It's querying servers across the globe seamlessly. Also, you don't have to memorize some random string of numbers like 142.250.190.46 just to check your email.
Right after relying on that DNS translation to secure a destination address, the packet utilizes TCP/IP. These are the essential standardized communication protocols of the Internet. Now, why is this absolutely crucial? Because the Internet is made up of incredibly diverse, often totally incompatible systems. Let's paint a picture. Imagine you're using a slightly outdated 10-year-old smartphone on a spotty cellular connection, and you are trying to pull data from a state-of-the-art Linux super server that's housed in an underground bunker in Iceland. Without a shared framework, those two machines would just be shouting digital gibberish at each other. TCP/IP acts as the ultimate diplomatic translator. It provides the standardized language that ensures these totally different computers can actually understand each other once they finally connect. It really is the universal language of global connectivity.
Now let's dive into part 4, the TCP digital handshake, agreeing to communicate.
We've officially reached the climax of our packet's journey, the crucial moments right before any actual web page loads. Our data packet has navigated the routing maze and arrived at its destination. But diverse systems don't just instantly start dumping data onto your screen. First, they meet. Then, utilizing that TCP/IP standardized language we just talked about, the systems have to negotiate. This rapid, structured negotiation is a literal three-step conversation known as a three-way handshake. First, your computer sends a SYN packet, short for synchronize, basically asking, "Hello, can you hear me?" The receiving server then responds with a SYN-ACK packet, synchronize acknowledge, replying, "I hear you, can you hear me?" Finally, your computer sends an ACK, or acknowledge packet confirming, "Yes, let's talk." Only after this highly specific microsecond sequence is successfully completed to guarantee they're playing by the exact same rules will a single image or line of text be sent back to your device.
And finally, Section 5, Connecting the World Wide Web, Reaching the Final Destination.
After navigating that massive routing maze and executing that secret digital handshake, our data packet finally arrives. And this brings us to a really crucial realization from our source material. To quote it directly, rather than viewing the network as an abstract concept, the source emphasizes the physical and logical architecture that supports the modern web. This whole journey serves to remind us of something profound. The seamless, instantaneous global connectivity that we completely take for granted, it isn't magic. It's the direct result of billions of fragmented puzzle pieces hurtling across the globe, undergoing strict multi-step handshakes, and reassembling on your screen perfectly in the time it takes you to blink. It requires highly specific sequences, physical hardware, and standardized rules all working flawlessly together.
As we wrap up this explainer, I want you to just think about the device you're watching this on right now. Underneath this everyday digital miracle are miles of physical wires lying in the dark on the ocean floor, combined with extremely delicate mathematical agreements happening millions of times a second. So, with billions of these complex digital handshakes happening in your pocket every single day, relying heavily on both physical cables and logical codes, is this standardized global network brilliantly robust, or is it incredibly fragile? I'm going to leave you with that thought. Ponder the sheer scale and the hidden reality of the architecture making this very explainer possible for you right now. Thanks so much for joining me to demystify the internet, and remember to keep asking questions about the technology you use every single day.